move to the second speaker. The speaker is Matthias Early. The title of his presentation is Cooling of a Linear Induction Launcher. So please.
My project was centered on the use of cooling to change the velocity of a linear induction launcher. Basically, the best way to explain what a linear induction launcher is it's basically a magnet that has a current run through it for a very short period of time to create an electromagnet, which pulls an object, a ferrous object, forward, at which point it stops being an electromagnet because it only acts as one for a very short period of time, and the object just keeps on going. So my hypothesis was that cooling the linear induction launcher would increase the velocity of the projectile. And basically, my idea was that I've heard about experiments where cooling the circuitry would allow the electronics to function better. And I was just trying to figure out how exactly it managed to do that and what exactly the effects were. This is my breadboard. As you can see here, the current flows in with around 5 volts, and it goes into this circuitry. Over here you have a timer switch which controls this transistor to turn the current on and off. So it's a pulsed charge, and it's basically alternating current. And once you have an alternating current, it can go through this transformer to bump up the voltage from 5 volts to 500 volts. Once it's at 500 volts, it goes into here, which is a rectifier, which the voltage is recorded. And once it's in this rectifier and it's converted to direct current, it goes into this capacitor bank, which charges up to between 200 and 240 volts. Once it's at the desired voltage, which I kept at an average of 240 for my experiments, this button is pressed, which causes 2,000 volts to go into this plasma switch. The plasma switch functions by, once you have plasma, it's able to complete the circuit, allowing for the electricity to flow through this coil, creating an electromagnet which fires the projectile. Here's my schematic. As you can see, there's the 5 volts and my timer circuit and everything else. Over here is where the launcher is. Basically, for my tests, I created a small chamber using a yogurt container in which the induction launcher was placed so that I could control the temperature by adding different substances to the environment. The difference, yeah. Anyway, basically, to record my results from room temperature, ice, and dry ice, I recorded the sound of it firing. Here's where it was fired out of the tube, and here's where it's hitting its target. I recorded it on my iPod. Anyway, once I had the sounds, I just put them into Audacity, and I got the time. These are my results, which are actually quite interesting. Over here, you have the velocity plotted against the temperature. So as you can see, at room temperature, the velocity is quite low, and as it gets colder, the velocity goes up. There's an inverse correlation between the velocity and the temperature. Over here, this green line is the linear regression, which is basically the average velocity, and it's showing how it would continue up until the point that reached zero resistance, at which point it would no longer apply because it would flatline. Over here, you've got the velocity of projectiles plotted against the coil resistance and the temperature. As you can see, the velocity, as the velocity increases and the temperature decreases, the coil resistance is also decreasing. So basically, the reason it's going faster is because when the atoms are colder, they're closer together because there's less movement and less jittering, because atoms are constantly in movement, and when they're moving less, they're able to transmit their electrons easier because they're closer together. And basically, that's my results. So my conclusion was that the projectile speed was inversely proportional to coil temperature, which means colder is faster. And I would like to thank the Advanced Institute for Material Research at Tohoku University for sponsoring my trip to Japan. I really appreciate that. Thank you very much.
Thank you very much. So, question, comment? Maybe Dr. Takayama, could you make some advice to the him?
So congratulations on your research, and maybe you used the liquid nitrogen, so very low temperature, so minus 100 degrees. But how do you?
How did I know that it was that temperature?
Yeah.
I actually had an electronic thermometer outside of my closed system, so that I could monitor it without affecting the temperature. And basically, I made sure that it was at a uniform temperature, and if it deviated from that uniform temperature, I did not use that in my test results, and I added or subtracted ice or dry ice to get it back to a uniform temperature.
Okay, I see. And so that result is good, but very, very low temperature. So how we can application for
the real world?
Yeah.
Oh, for instance, you could run trains underground rather than running them on the surface to keep the temperature lower, because when there's a lower temperature, there's more efficiency in an electric engine, and for the magnetic levitation, you could run the same system with less energy, and it would be more efficient.
Okay, thank you.
Thank you very much. So the last speaker is Vishnu